Okay, as it talks in your textbook, acids and bases are very common solutions that we deal with lots. Certainly in the chem lab we do titrations and we do lots of experiments that involve acids and bases. So we want to talk about a few definitions of acids and bases, and then later we'll do some calculations on each. The definitions of acids and bases will be further refined when you go on into another chemistry class. To begin with, we'll look at Arrhenius acids. I'm not sure if that's the exact way to pronounce it, but it sounded good. So we'll look at the definition of Arrhenius acids, how they come to be. We'll look at more general descriptions of acids and bases. We'll look at something called the hydronium ion, and then maybe we'll look at a little bit of neutralization as well. So to begin with, here's a couple of examples of acids and bases. Hydrochloric acid, one of the standard ones, we have that in our stomach. And over on the right, that's a watch glass filled with sodium hydroxide. And these two nasty substances are examples of an acid and a base. Let's look at some properties. Maybe looking at these, this hydrochloric acid, clear, looks like there's not a whole lot there. Looks just like water, but I wonder what kind of properties it has. Similarly with sodium hydroxide, you may know some of them. Just take a second to look at these properties and see if you can determine which goes on which side. You'll want to pause your recording and just sort of see, just glance down at each one and move it from one side to the other side and see which ones you think are properties of acids and which are properties of bases. I'll just pause and then we'll start again. Okay, hopefully you paused and looked at those. Interestingly enough, things that feel slippery are bases. Had an experience when I was young cleaning grout on bathroom walls, and the cleaner that we used was very basic and it was slippery to the touch, and we didn't think much of it, but after the first day we realized that that slippery feeling, what was happening, was actually eating the skin of our hands, and so the tips of all of our fingers were almost worn raw from the base cleaner that we were using. Bases usually feel slippery. Things that are corrosive, acid, that would be an acid. Reacting with active metals, typically acids do that. Something that reacts with acids, yeah, probably be a base. Something that tastes sour, you can think about that. Think about a lemon, and lemons have acid in them, lots of acid, and that would be a sour taste. Something that reacts with carbonates. I looked online for that, and they say that bases can react a little bit with carbonates, but I'm not sure how much. Typically, we would talk about acids reacting with carbonates. Changes color of vegetable dyes. I'm not positive about that one, but I don't have many on bases, so maybe I'll put it over there. Or maybe I'll put it in the middle. But you could look that one up, see which property it is. Neutralized by bases, that would be an acid. Things that taste bitter, a base tastes bitter. Known as alkalis, another example of a base. Turns red litmus blue, or turns blue litmus red. One is, one goes one way and one goes the other way. It's actually this, a base will turn red litmus blue, and an acid turns blue litmus red. Just a quick note on how you remember that. An acid turns blue litmus red, and a base turns red litmus blue. So if you remember the ABR or BRB, be right back, then hopefully you remember which is which. So those are just some quick properties of both acids and bases. Now, when we get down into sort of the nitty-gritty of why does an acid exhibit those particular properties, this is what this guy Arrhenius said. He said that acids ionize in water to produce a hydrogen ion and a particular anion. So, for example, if I have hydrochloric acid, if I put that in water, it would produce a hydrogen ion, and it would produce the ion that goes along with that, the anion. So the chloride ion would be the anion. And a base ionizes in water. So if I had a base like sodium hydroxide, it ionizes in water, to produce hydroxide ions and a cation. So that sodium would be the cation. And a neutralization reaction then would take the hydrogen ions or the proton from the acid and react it with the hydroxide ions of the base. And that's what a neutralization reaction is, what it's defined as being. Now, if you're not sure if something is an acid or a base or not, you can check your periodic table or the data booklet that you've been provided with or that you purchased. Here on this side or in that column are a listing of all the common acids. And here are a listing of, not all of them, but many of the common bases that are around. There'd be other ones as well, but these are some of the commons. So this chart here is an acid. This chart here would be bases. So if you're not sure if something's an acid or not, you can always check your data booklet. So a further refinement to what Arrhenius was talking about when he said that an acid produces a proton is that, and you'll talk more about this definition in a later course, but I just wanted to introduce the concept here, is that we do talk about acids as being ones that produce protons, that have protons in them, so a hydrogen ion, or I guess we often call that a proton. So if I see a hydrogen ion or a proton, I'm thinking acid. But another substance or another species that is often used to describe an acid is something called a hydronium ion. And a hydronium ion results from the production of a hydrogen ion or a proton. So basically, if I have an acid that I introduce water to, it dissociates or ionizes, the HCl ionizes into hydrogen ions and chloride ions. But then immediately that proton or that hydrogen ion will react with water. It seems a little funny, but it'll react with water to form, notice there's one hydrogen here and there's two there, so they'll react together to form a compound that has three hydrogens in it. So it'll be H3O+, and that species or that entity is known as a hydronium ion. Okay? So acids, if you think hydrogen ion, you think proton, you think hydronium ion, all of those are associated with acids. We also will be talking in the next Scribblecast about the strength of acids and a way that we can quantify that, put numbers to it. But it's also useful to talk about a strong acid versus a weak acid, or a strong base versus a weak base. So strong acids are things like, if you look on your chart, there's a little line here. And the little line there indicates anything above that we typically call a strong acid. So things like perchloric, hydrochloric, sulfuric, nitric, all those guys there are strong acids. Ones that fall below that would be, like here's one, ethanoic acid or acetic acid, and vinegar is a dilute form of acetic acid. But those are examples of weak acids. Okay, so things above the line, strong acid, things below the line, weak acid. Oh, am I recording? Sorry, I'm recording again. So, strong acids, weak acids. So, for an example of a strong acid would be hydrochloric acid. That's a strong one. And the reason why it's strong is due to the amount of dissociation or I guess ionization might be the proper term, ionization into hydronium ions. So these ones up here are strong because they ionize into hydronium ions. Almost all of them immediately go into hydronium ions. Whereas these acids down below, a portion of them will go into hydronium ions, but not all of them. Not all of them. These numbers over here, we used to use a percent, but these numbers here, actually that's a quantitative way of describing how much dissociation or how much ionization actually occurs. So strong acids, large dissociation. Weak acids like ethanoic acid, like this one, this would be an example of a weak acid. It dissociates very little. Example, if I have a strong acid and I put that on my jeans, it won't take long before I'm going to have a hole in my jeans. If I take ethanoic or acetic acid, put it on my jeans, they're probably, I haven't tried it, I guess you can try it if you want, but I doubt whether it would eat away the jeans very quickly. You'd probably just have your jeans smelling like vinegar for a while. Okay, so strong acids, a high degree of dissociation, weak acids, a low degree of dissociation. Now, compare that with concentrated versus dilute. That's an interesting thing to look at. Like we looked at a strong acid versus weak acid, highly dissociated, weakly dissociated. Then compare that with something that's concentrated versus dilute. It's a different concept. So concentrated versus dilute, what we're looking at is the amount of substance per volume of water, not how much dissociates. So we could conceivably have something that's a strong acid, but it is put in a lot of water, so it's dilute. So it's not very concentrated. So I could have a strong acid, but it's in a dilute solution. Or I could have a weak acid, but it's in a concentrated solution. So it may be a weak acid, but I got lots of it, as opposed to this first one where I had a strong acid, but I had very little of it because it was dilute. That might be something to look in the textbook and research a little bit, just that difference between the strength of your acid versus the concentration. Because those two ideas are different. I can have a strong acid, but it could be concentrated, very concentrated, or it could be dilute. And similarly, I could have a weak acid, one that dissociates very little, but it could also be in a concentrated form, or it could be in a dilute form. Okay, so it might be worthwhile to review that, just those ideas a little bit. Now, the last concept I wanted to look at in this scribblecast deals with multiprotic acids. And there are some acids or some species that will actually donate 2 protons. I guess there's one that, or there might be one that has 4, I don't know of it, but there's one that will donate 3 protons. So something called a multiprotic acid means that I have an acid that is capable of giving away 2 protons. And if it gives away those protons, that is what is making my acid. So for example, I have sulfuric acid here, H2SO4, and notice when I react H2SO4 with water, I'm going to give up one of those hydrogens to the water, so that will become a hydronium ion. That's my acid part, right? And then this thing, if it loses a hydrogen, will become not 2, but just H1SO4. So this is an example of a, I guess that would be the anion that goes along with this. Anyway, this substance here, the bisulfate ion, also has another hydrogen. So I could take that and I could react that again with water to perform a hydronium ion, which again gives me acid. And if I lose that hydrogen, it'll become a sulfate ion. So some acids like H2SO4, phosphoric acid, is another example of one that can give away multiple hydrogens. Though this is an example of a multiprotic acid. Typically, the process of giving away those hydrogens, though, it's very easy to give away the first one, and so that would make it a strong acid. But when it gives away the second one, it's a little bit less likely to give away that second one. So this one here would probably be classified as a strong acid. But if I look at this one, it's probably on the chart under the weak acid. So it's still an acid, but it's a weak acid. It won't give that hydrogen away very quickly. So that's just a quick introduction into some definitions of acids, looking at an Arrhenius acid, and looking at that concept of hydronium ions.